you follow the steps. Because we said for ballistic pendulum, momentum is always conserved, and momentum is only conserved in the horizontal components. Momentum is only conserved in the horizontal components. Why not on the vertical components? Because we said momentum is only conserved if there is no external force acting on the system of colliding bodies. So here we can see that there's going to be weight, so which means it's going to affect the what? The momentum of the system. So momentum is only conserved in the horizontal component, because in the horizontal component we are going to have only the two systems, the bullets and the wooden block. That's why we're saying momentum is conserved here. And when it's at this point, horizontally momentum is not kinetic energy is not conserved, but kinetic energy is conserved in the vertical component. Why? Because there's an aspect to do with the mechanical energy, because mechanical energy is a combination of kinetic and potential. Why are we saying our momentum is not, kinetic energy is only conserved at this point, at the point of swing, when it's swinging? Okay? Are we together, members? Are we together? Members, are you following me?
Yes. Yes.
Okay. So after sketching this, so the only thing we are going to change from here, they've given us the mass of the wooden block is 2 kilograms, and the bullet is 40 grams. It's almost the same question. So the only thing is here. So you have to find the height, because we say to find the angle. The angle is given by cos theta 2GEL minus b squared over this. So the length was given. And we say that the angle of swing does not depend on the height. Does not depend on the height. It depends on the what? It depends on only two factors. One is the length of the string. Then the second one, the speed of the bullets. Those are the only two factors that affect the angle of the swing. So cos theta is equal to 2GL minus v squared. So how are you going to get this v squared from? You're going to get v squared from the principle of conservation of linear momentum. You're going to get it from the principle of conservation of linear momentum. And I've worked it somewhere here. I've worked it out here. So you can see. So mu is equal to m into, because they were moving with a common velocity. So v is the common velocity. V is the common velocity. So v is equal to mu over m plus capital M, where capital M, small m is the mass of the bullets. This is the mass of the bullets of the petlet. Then capital M is the mass of the wooden block. Is the mass of the wooden block. So then you substitute, you get your final velocity v here. This is the final velocity which the two bodies will move with. Then you substitute it here, you get your answer is 53.4 degrees. I said for accuracy, you put your answer to 3 significant figures. 3 significant what? Figures. Or to 1 dp. That's the accuracy. That is the accuracy you must take note of. So then in second part, they're asking, state the factors on which the angle of swing depends on. We said it depends on how many factors? Angle of swing is affected by how many factors? Factors affecting the angle of swing. Factors affecting the angle of swing. Because we said, actually you can get it from the formula that we have just generated, where we said cos theta is equals to 2GL minus v squared over 2GL here, this one here. So you see that 2 is a constant, G is a constant, L is not a constant, which means the two factors which will affect the angle of swing is the length of the string. The length of the what? Members, the length of the what? Of the string. Are we together, Peter? Are we together, Baptist? Yes? Members, are you following me?
Yes.
Okay. So the length of the string. Then the second one is going to be the speed of the bullets. The speed of the bullets. The speed of the bullet. So those are the two factors that will affect the angle of swing. So that's what I was expecting in that question. That's what I was expecting in that question. Maybe to summarize it up, let's do this one of UNEP of 2006, just to give us the last summary on that. Are you seeing this question here? Am I highlighting? Are you seeing this question? Am I highlighting, members? Are you seeing this one? This one here. where I've said a bullet of mass 0.1 kilograms moving horizontally with a speed of 420 meters per second strike a block of mass 2 kilograms at rest on a smooth horizontal or on a smooth table becomes embedded in it. Find the kinetic energy lost if they move together. So they want us to find the kinetic energy. They want us to find the kinetic energy lost. So we said for inelastic collision, because this type of collision is inelastic in nature. It's in what? Inelastic in nature, which means the two bodies will move with a common velocity. They will move with a common velocity. Why? Because they will stick together. This one, they stick together. They stick what? Together. So if they are moving with a common velocity, so you find that our sketch now here will be, so it will be like this. So this would be our sketch. This should be our sketch. This should be our sketch. So I'm assuming this one before impact. And that's why I'm using dotted line. This one is before impact. So a gun was fired from certain point here and is moving with a given velocity, u. So after impact, it raised up to a given height, So now they have said is embedded. So the bullet is inside now, So it is raised to a given height, from where it was before. So this height is h, and is moving now, is swinging with a common velocity v, So this is the angle of swing, theta. That's the angle of swing, theta. So this one is capital M, which they have said from the question they've given is 2 kilograms. Then this is small m, which they've given is 0.1 kilograms. Are we together, members? Are we together? Members, are we together? Baptist. Apire. Hello? Members, can you first unmute? And talk to me, please. I want to see whether we are moving together, because this one we are just doing recaps. Are we together?
Yes, sir.
Okay. So they want us to find the kinetic energy loss. But for us to find it, we know that kinetic energy is only conserved in the vertical components. Mechanical energy is conserved in what? In the vertical components. So for us to find, we have to find this velocity v. So we can say from the principle or from the law of conservation of, of linear momentum, which means total momentum before collision must be equal to total momentum after collision. So before collision, we shall have mu equals to, because this one is already 0 because it's at rest. This one is at rest. So which means the initial velocity there is 0. Equals to, now they are moving together. So it becomes m plus capital M times the common velocity. Why do we do that? Because I want to find v. Because for me to find the energy lost, I need to find the velocity, because kinetic energy depends on the velocity of the body. So I need to first find the common velocity after collision. So mass of the bullet is 0.1 times the speed, which was given to be 420, equals to 0.1 plus 2.0 times v that we are looking for. So you find that if I'm from here, if you are to make v the subject, you can find our v equals to mu over m plus capital M. That's also another way. So you find that our v will be equals to 0.1 times 420 divided by 0.1 plus 2. So what do we get? So start off 0.1 times 420. So we get 42 over, this is 2.1. So what do you get? Divide by 2.1. So we find we shall have our 20 meters per second. So which means after impact, the two bodies, the bullets and the wooden block, will move at a speed of 20 meters per second. But that's not what they're asking for. They're asking us to find the kinetic energy loss. But you cannot find the kinetic energy before finding the what? The final velocity of the system, the combined velocity. So now we shall say, So what will be kinetic energy before collision? So kinetic energy before impact. Kinetic energy before impact. Before what? Impact. What will it be? What will be kinetic energy before impact? So kinetic energy before impact, I will be equals to a half mu squared. Mu what? Squared, because it's only the bullet which is moving. So it's a half times 0.1 times 420 squared. So kinetic energy before we shall have 420 squared times 0.1 divided by 2. So it will give us 8,800 what? 20 what? Joules. That is before, that is kinetic energy before. Then also kinetic energy after impact. Kinetic energy after impact. So kinetic energy after impact will be, after or final will be a half into m times capital M v squared. Members, are you following me? Members, are you following me? So kinetic energy
Yes.
will be equals to a half into 0.1 plus 2. Then time the final velocity which we have got is what? We have got what? 20. So 20 squared. So this one will be a half times 2.1 times 400 times 400. So kinetic energy, the final kinetic energy will be so 20 squared times 2.1 times 2.1 divided by 2. So we find out we shall have 420 what? Joules. We shall have 420 joules. That is it, the final one. But they're asking for the kinetic energy loss. So we know that kinetic energy before collision is always greater than kinetic energy after collision. So kinetic energy lost will be equals to kinetic energy initial minus kinetic energy what? Final. So which will be before what? 8,820 minus 420. The answer we get must be in joules. Must be in joules. So what do we get? What do we get? So 8,020 minus 420. So if final we shall get 8,000 for what? 400. What? Joules. Have you seen that? Members, have you seen that? Yes, have you seen that, members?
Yes.
So that's how you are supposed to approach the question. That's how you are supposed to approach that question. So the rest, now as an A-level student, you don't need to be told. I've already guided you on all these questions. So get time and start going through this question one by one. Go through them one by one, one by one. We have discussed all of them.
Excuse me, teacher.
Yes, please. Yes, Sandra.
Teacher, I was asking, I've seen that question there that state the work energy theorem. What is it about?
That one we are going to answer it under work energy and power. Okay. Okay.
Yes.
Because this one they were just giving according to UNEP setting how the question was appearing, but we have not yet looked at that. We are going to look at it under a work energy theorem. Okay. Okay.
Yes.
But if you want the answer, I can give you. Before even, can I give you the answer?
It's okay. Let's first talk about it.
Okay. We shall look at under this one, because under solid friction we shall start looking at work energy and power. Okay.
Yes.
Yes. So subheading, can we look at solid friction? Solid friction. So Sandra, for you came late. I was still doing recaps of what we have learned the other time. Okay. Okay.
Yes.
And doing some of the exercise I gave. I think, was it you? I got someone submitted the work. Or was it you or Sandra? I mean, Brenda, sorry. I got the work, but I can't remember exactly. And for you, I think it was,
mine have not.
You did not submit.
I never submitted. Yeah.
I think it's from Brenda. It's from Brenda. Okay. Solid friction. Let's look at solid friction now. Solid friction. But Sandra,
Yes, teacher.
you have understood what we have the ballistic pendulum, not so?
Yes.
Okay. Okay, let's look at solid friction. Let's look at solid friction. We know that friction is a force. We know that friction is a force, not so? Friction is a what? Is a force. That's the key thing we should note there. So we said friction is a force that opposes relative motion of two surfaces in contact. So that's the definition. So definition, friction is the force that opposes relative motion of two surfaces in contact which means for us to realize friction does not take place. Solid friction does not take place in space. It takes place between solid surfaces. Like a book and a book. If you put a book on a table, so those two are solid, which means we shall experience solid friction. Unless, even if the surface is smooth like what? There is friction in there. But the only thing that sometimes when we are doing calculation, the frictional force is too minimum that can be neglected. That's why sometimes we said it's a smooth surface. It's a smooth surface but does not mean that there's no frictional force. The friction is there, but it's too minimum to the extent that it can be ignored. Right together. But whenever two surfaces are in contact, there's frictional force. Even in space, even in liquids, there's friction. But we have different names we give them. In air, we call them air resistance. We call them what? Air resistance. Then in liquids, we call them viscosities. So all the stages of matters experience friction. But what type of friction? If it's between solids, we call it solid frictions. We call it solid what? Frictions. If it's in air, we call it air resistance. If it's in liquids or in fluids, we call it viscosities. So you should take note of that. But for now, or at the moment, we are still looking at friction between solid surfaces. So now, what are the type of frictions? We have two types of frictions only. We have what we call static friction and then kinetic friction. Static means something which is not moving, is at rest, is stationary. Okay? So, like now this one here. If I put it like this, the frictional force between these two surfaces, because it is at rest, the type of friction which is here is what? Is static friction. Is static what? Friction. So type of friction. We have static friction, or stationary friction. Static means something stationary, which means is at rest. Two bodies are at what? At rest. Then we have kinetic friction. Or sometimes we call it dynamics. Dynamic friction. Dynamics is something in motion. In what? In motion. So the frictional force experienced by bodies which are in motion, we call it dynamic friction or kinetic friction. So frictional force experienced by bodies which are at rest or is stationary is a static friction. So let's look at the first one here. Definition: static friction. So we are saying static friction is a frictional force, should be like that. Or you can say is a force. Is a force that opposes the tendency means the ability of a body to move, the capability of a body to move, of a body to slide over another, So you can say is a frictional force, static friction is a frictional force that opposes, or is a force that opposes the tendency or motion of solid surfaces to slide over another. So that's another way you can state it. Are we together, members? Are we together? Yes. Then we are saying there's also what we call limiting friction. Limiting friction is the maximum frictional force between two surfaces in contact when the relative motion is just starting, is just starting, is just starting, is just starting. So what do we mean by that? What do we mean by that? So let me try to show you some video here so that you can see them. What do you mean by that? Let me try to show you some video here so that you see what is static friction. Members, members,
Yes, teacher.
are we together?
Yes.
Mhm. Get you a good video. Let me get a good video. Yes, members, members,
Yes, teacher.
go through this. Let's go through this video. Follow the video carefully. Members, members,
Yes.
are we following?
Yes.
Okay. This one is just to summarize because I don't want us, when we come back to the notes, I don't want to take a lot of time on that because this one you can read through. That's why I'm trying to show the video. Okay. So after this, we're just going to look at the experiments. Okay. Are you together?
Mm.
Yes, because these are the,
Mm.
yes. Okay.
So can you adjust the volume?
Can you draw that graph? Members, can you sketch that graph? Draw that graph, please. This graph is very important. Sometimes they ask for them. Okay. Okay.
So I'm not hearing the voice.
Okay. Can you sketch this graph? Sketch the graph. Sketch that graph. So the graph is like this. Mhm. So this is frictional force. Then this is a force applied. So members.
Yes.
What I wanted you to extract from that video was only the graph. That's what I wanted you to extract from there. So let me explain the graph a bit. So we are trying to see, we want to compare the effect of frictional force with respect to the force applied. So we are saying that for the case of solid friction, like for static friction, the force applied is equals to the what? Is equals to the force applied. The frictional force will be equal because it depends entirely on the force that you have applied. Okay? So it increases with the force applied. This one shows that it increases with force applied. So this would be F, sorry, this would be F. It increases with the force applied. But for kinetic friction is directly proportional with the what? To the rest, to the what? To the normal reaction. So you find that solid friction, it keep decreasing, is less than the normal reaction. Is less than the normal reaction. That's why now we bring the aspect of limiting friction. That's why we bring the aspect of limiting friction now. Because limiting friction is the maximum frictional force between two surfaces in contact when the relative motion is just starting. It's just starting, which means it's already just starting. At that point, we can't call it we can't say is a kinetic friction because it's just starting. It's just sliding. It's just about to slide. So that point we call it that for calculation purposes we use limiting friction because we can determine that one mathematically. And another thing you should also note from this concept is that there is no perfectly smooth surface. There's no surface which is perfectly smooth. Okay? I together members. There's no surface which is perfectly what? Smooth. So you must take note of that. That's why we make assumption. We assume that it's smooth, but that the frictional force is small to the extent that it can be ignored. So that is it. So kinetic friction is the force that opposes relative motion between two surfaces when the two bodies are in motion, which are already in motion, not about to start, but they're already in motion. Okay? Are we together, members? Are we together? Members, are we together? Yes. Okay, let's look at the laws of friction. What are the laws of friction? This one you have to be very careful with it, and it's very examinable. Laws of friction. Let's look at the law of friction. What is that? We cannot ignore whenever we are talking about friction. Even if you go to which part of the world, even if you go to which part of the earth, these are the things that still hold. There are no theories. There are laws. So we are saying that frictional force between two surfaces in contact opposes their relative motion. That one, there's no doubt in that. Whenever there's frictional force, it must oppose motion between two surfaces in contact. So the first one is the first law. Frictional force or frictional force between two surfaces in contact. It must be in contact between two surfaces in contact. Oppose their relative motion. Oppose their relative motion. That is the first law. Whenever two surfaces are in contact and there is frictional force experienced or exerted, it must oppose the motion of those two bodies, of the two particles, or of the two surfaces. Then the second one, the second law, like we have seen from the video, frictional force does not depend on the area in contact. Instead, it depends on the normal reaction. You have seen from that equation, members. It does not depend on area. So you have seen from the video where we are watching. Did you see anything to do with area? Have you seen anything to do with area, members? No. So frictional force does not depend on the area. So we are saying the second law, frictional force is independent of the cross-sectional area. It's independent of the cross-sectional area of the surfaces. Cross-sectional area of contact of the surfaces. Provided normal reaction is constant. Provided normal reaction is constant. Provided normal reaction is constant. So that's the second law. You should know that here we are saying frictional force does not depend on the area. Frictional force does not depend on the cross-sectional area of the surfaces in contact. Then the third one, which also we have seen from the equation. So we are saying that the limiting frictional force is directly proportional to the normal reaction. Is directly proportional to the normal reaction or to the normal force. Some people call it normal force or normal reaction. But independent but independent of the relative velocity of the surfaces, but independent of the relative velocity of the surfaces of the surfaces. Those are the three laws that govern friction. Those are the three laws that govern friction. So they will ask you state the laws of solid friction. State the laws of solid friction. So this is what they are asking for. The first one, frictional force between two surfaces in contact oppose their relative motion. Or you can say frictional force opposes relative motion between two surfaces in contact. It's still the same thing. Then the second one, the frictional force is independent of cross-sectional area of contact of the surfaces, provided normal reaction is constant. Then the third one, the limiting frictional force is directly proportional to the normal reaction, but independent of the relative velocity of the surfaces. So frictional does not depend on the speed, does not depend on the speed, and does not depend on the area. So our time is running out. So we shall join back and then we continue from there. Is there any question, members? Is there any question so far on the laws? Is there any question? Brenda Nakachwa. Brenda,
Yes, teacher. Yes,
what happened? You came late.
teacher. I didn't know that there was a lesson at this
Excuse me.
time.
Brenda, that's a funny excuse you have ever given me. Okay, our time is running out. Our time is running out. If there's any question, you can raise it in the second session, okay?